Hi everyone. Hope you're enjoying your snow day. It was looking pretty nasty earlier today, but looking like it's pretty blue out right now. So hopefully they're ready to continue our lectures. We're going to keep moving forward. We need to keep up with the syllabus. So what I want to do today is we're going to finish up chapter 14. That's going to be on our kinetics of reactions. So we're finishing up with reaction mechanisms. For the last week and a half or so, even including before break, we talked about how do we observe reactions to determine the rate laws, the rates, the order of the reactions, and also the reaction constants, right? So these are all macroscopic observations that we have made of particular reactions. What we're going to learn is how to combine everything we just talked about and turn it into a microscopic picture of what is actually happening. So we know from the kinetic theory of matter that it's not magic when two molecules get close to each other that they react. We learned on Monday that two molecules or three molecules or however many molecules that need to react need to come together in such a way that the reactants do form a product, right? They need to collide in a orientation in which is favorable for the reaction to happen, so it needs to be in a correct orientation. That was our A factor that we were talking about in the Arrhenius equation. And they also need to collide with enough energy to overcome the activation energy to form the transition state that will eventually form the products. So we're going to pull all of these ideas together that we have so far. Just basically, I feel like we've been learning to just do the math on, right? How do I do the experiment? How do I get these numbers? Well, let's turn it into something physical, something that we can say, this is how these molecules are coming together. And the way we do that is called proposing a reaction mechanism. So what you will find as you go further in your career, if you're becoming a scientist, that reaction mechanisms can only be proposed. They can never be proven. We have never seen a reaction mechanism. All we can do is propose based on the data that this is what we think is happening. And in fact, we have some instrumentations that can see very, 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 very quickly. We're talking about fractions of a fraction of a fraction of a fraction of a second, down to nanoseconds. And sometimes you can actually see these transient transition states. So we do have evidence that transition states exist. We cannot trap them. We've talked about that before. But again, we can only propose these mechanisms. We can never prove them, or at least without the technology that we have currently. So let's get some definitions, right? I keep mentioning the word or the phrase reaction mechanism. So let's define it. You can see on the slide it says it's a sequence of reaction steps that describe the pathway from reactants to products. Okay, that kind of makes sense. We were drawing on the board before. We had our reaction diagrams where we started with reactants. We drew this kind of like a hill-shaped object, which was our activation barrier, which is the activation energy, it leads to transition state, and then it drops down, and then it forms a product, right? For most of 1101 and 1102, we've been looking at balanced chemical reactions where we start with our reactants, we end with our products, and we say, hey, good, that's all I care about. How much did I start with? How much did I end with? What we have not discussed is how that actually happens, right? And so this is what we mean by a sequence of reaction steps. So even though we overall describe how we started and how we ended, there's well, not always, but there is usually a lot of other motions, movements going on in between. Our bonds breaking, our atoms moving, our bonds forming. How is this actually happening? And so this is what we define as elementary reaction steps. So it's a single step in a reaction mechanism. So it's saying, okay, I have this one process, and then I have another process, and then I have a third process. They don't always need to happen in a particular order, though most chemical reactions do happen in a particular order. If you go further in biology, you'll find out there's a lot of different ways to combine things, especially with enzymes acting as a catalyst. But they all happen in these elementary reaction steps. So a single step in a reaction mechanism. So let's pull apart this reaction of NO2 reacting with carbon monoxide to form NO and CO2. So what we're used to seeing, oops, I skipped ahead too far, but here we go. We're used to seeing this bottom part down here, where we say overall we have 1 mole of NO2, or 1 molecule of NO2, is reacting with the carbon monoxide to form the NO. I don't know why they keep skipping forward. There we go, the NO and the CO2. That is our overall reaction that we're used to. Experimentally, we have found out that there is other smaller intermediate steps that are happening that contribute overall to what we see. We know what we started with, we can measure that. We know what we ended with, we can measure that. We are going to see that not all reactions are elementary reactions. Not all of them happen in one step, right? And so keep in the back of your mind when we're talking about how rate laws, which we said rate equals K times some of the reactants raised to some power, right, does not always equal the coefficients in front of the reaction. And that's what we're going to see with this reaction. So let's keep this in mind. Let's break it down real quick. The first step of this reaction is actually, there's no CO involved, even though it's part of our overall reaction. One NO2 molecule reacts with another NO2 molecule. There's an oxygen transfer between the two, so one becomes NO, so that one transferred its oxygen to the other NO2, which formed NO3. So we made these distinct intermediate products. Whatever the reaction rate is, as soon as that NO3 is formed, based on its K, its reaction constant, it will statistically react with the carbon monoxide that's in this same reaction vessel. So now we have an NO3, which is never part of this product side, or sorry, this reactant side of the equation. This NO3 is then what is responsible for reacting with the CO. And then we see there's another oxygen atom transfer. So that NO3 transferred an oxygen atom to the CO. That leaves the NO2 and formed the CO2. We'll get back in a second to adding this all up, but let's take a look molecularly what's happening and see if we can break this down and relate it to the Arrhenius equation. So we said this was a two-step mechanism, and again, it's only a proposal. There's no proof that this is exactly how it happens, but we do have experimental evidence to support it. But it looks like that two NO2 react, and as you can see here, they're in two different orientations, which is again what we were talking about with that Arrhenius equation, where that A factor, that pre-exponential factor, the collision frequency factor, that determines how often, it's statistic, right? You have trillions of molecules, but it's saying how many times or how frequently do these two molecules collide in the correct orientation. So you can see that the molecule on the left is in correct orientation with the molecule on the right. And you can easily see here that there's an oxygen transfer step. So we're left with this NO2. It broke this NO bond. The NO then formed a new bond over here. So that's our first step. And then this NO3 went forward, collided with the CO molecule. So there's your carbon monoxide. There's this intermediate product that we formed. Another oxygen transfer reaction happens. We're left with the NO2. That oxygen was transferred for the carbon monoxide and formed carbon dioxide. So that's one new definition that we're learning. So we talked about before how you cannot isolate a transition state. So the transition state being that transitionary period where it's kind of forming bonds, kind of breaking bonds, where it's at the top of that energy diagram. You cannot isolate a transition state. When we talked about catalysis the other day, we saw it when we had multiple activation energies and we kind of had a well between the two. This is that intermediate period where this NO and this NO3 are actually, if you were quick enough, you could isolate these two because these are stable products. But we know this NO3, based in this environment, is going to immediately react with the CO. Well, I say immediately because we know it's a fast reaction, but depending on how quick or how large that K is, that reaction constant K, it's going to find a CO and react fairly rapidly to form the final products. But it is possible to isolate these intermediates. It is not possible to isolate. So if imagine we have this first step where this bond right here between the N and the O is partially broken and this N and the O is partially formed, that is impossible to isolate. We can isolate something like this. So that's a take-home message about mechanisms. But we've broken this down, so let's see why this is important. Why the hell do we even care, right? So let's take a look. Reaction mechanism. Let's add them together. So we said our first elementary step, NO2 plus NO2 yields NO plus NO3. Well, that's what I see right up here, right? My second step was my NO3 plus the CO yields NO2 plus CO2. Again, that's what we saw physically here in step 2. Let's see when we add these two elementary reactions together. What we'll notice is that on both sides of the equation, we have an NO3. This is called our reactive intermediate, and this is what I was alluding to in the last slide. It's formed in one step and consumed in a subsequent step. It is possible to isolate in very low amounts, though it's usually difficult, but it is not usually represented if we go back, in the overall reaction. But it is a product that is formed. We'll also notice that an NO2, so we say, oh, well, if I add everything up, I should have 2 NO2 on this side, right? Plus a CO, so there's 2 NO2 plus a CO. But again, if we take into account and do due diligence doing mathematics, we'll notice there's an extra NO2 over here, where mathematically it cancels out with this one of these 2 NO2s. So overall, it's only one molecule of NO2, excuse me, reacting with one molecule of CO to form one molecule of NO plus CO2. Because this NO2 is regenerated, it is not as counted as being consumed. That's why. So our next idea that we want to tackle is molecularity. And so what does this mean and how does this play out? So molecularity is discussing how many molecules are colliding in each step. So sometimes if we had this as one reaction and we said this is 2NO2 forming NO plus NO3, and since it's an elementary reaction, the molecularity is actually just the coefficient, because we could write this as 2NO2 yields our products. That is not always the case, because sometimes, like we see here, the overall reaction doesn't equal the molecularity of the reaction. So let's figure out what's molecularity. So it's the classification of an elementary reaction, so specifically an elementary reaction based on the number of molecules, and sometimes atoms, on the reactant side of the chemical equation. It's saying how many molecules or atoms need to collide at a singular moment to form a reaction. Here we see that there needs to be 2 molecules of NO2 present to form this elementary reaction. There needs to be 1 molecule of NO3 and 1 molecule of CO to form that. So we have a molecularity of 2, a molecularity of 2. We cannot assign molecularity to an overall reaction because it's combined of several intermediate steps, these elementary reactions. You can only assign molecularity to elementary reactions. So let's break these down. Let's increase our definition of molecularity. So let's look at this. So we have an example of ozone, which is O3. And so you see it's O3 star. That just means it's in an excited state. It's been so it's not quite stable. It's got a little bit of extra energy. That's all we need to know. But it can spontaneously, under certain conditions, break down into molecular oxygen and atomic oxygen. So this is exactly what we see here. Given this excited state, this bond can break, and what it ends up forming is from O3, from ozone, can form O2 and O. We call this a unimolecular reaction, uni being one, molecular being molecule. So it is one molecule and it's forming products, right? So we don't care about how many products are formed, we care about our reactants and how many reactants it required to have that elementary reaction proceed. It took one molecule of O3 and that's it. So it is a unimolecular reaction. We can follow up this reaction with another term, a bimolecular reaction, right? So like the same idea. when we have a bicycle. So bimolecular being two molecules to produce an elementary reaction. So we'll use our example again. Instead of having an excited state of ozone, we can just have regular ozone. So you just see there's a lack of a star. So we will, not in 1102, but in other sections of chemistry, talk about what an excited state is. But we have a ground state ozone molecule. It reacts with one of these atomic oxygens, and so this is usually what we talk about when we put holes in the ozone layer, why it breaks down. So even though we have one molecule of O3 that's being affected, it breaks down into O2, an atomic oxygen. But look what happens when there's presence of atomic oxygen. This is really unstable. It reacts with ozone and pulls it apart into oxygen, molecular oxygen. So we'd call this a bimolecular reaction. Again, we don't care about the number of products we formed, but 2 products came together in an elementary step. And the elementary step is just this transfer of an oxygen between the two species. In general, most reactions are either unimolecular or bimolecular. The probability of having more than 2 molecules collide at the exact same time in space decreases very rapidly. It is possible to get termolecular reactions, so this is the idea of 3 molecules coming together in space at the same time with the correct orientation, with the correct energy. So you can imagine how statistically improbable, not that it's impossible, that reactions like this happens. Because it's statistically less likely, these reactions tend to proceed much, much more slowly than bi or unimolecular reactions. So again, we have an elementary reaction. And here we can see we have atomic oxygen, and we have 2 of those atomic oxygen atoms, plus 1, in this case, we're going to say M, it's a metal, right? So whatever metal gas we have. And if we form that, it basically ends up being in this case, it's going to be a catalyst, but we can see there's a reaction that happens. 1, 2, 3 things need to collide, because if 2 atomic oxygen collide, they're not going to react. It needs this 3rd molecule, M. And when that happens, we have this formation of O2 and a production of M. So it's just consumed, but it ends up being a termolecular reaction. So 1, 2, 3 reactants are necessary to come together to produce, we don't care how many products. So it's another elementary reaction, 3 molecules come together, termolecular. So let's see how this plays into rate law, right? So we see the rate law for an elementary reaction follows directly from its molecularity, because an elementary reaction is an individual molecular event. Well, it's kind of what we've been talking about, but let's see what this looks like mathematically, right? So before, if you look on the right-hand side of the screen, when we've been writing rates, we said we cannot ab initio, which means without additional information and without additional starting information, figure out what the rate law is by just looking at a chemical reaction. So we write a balanced chemical reaction. I have specifically told you you cannot determine the rate from that reaction. We've done a couple of examples where we've seen that's not possible. You can't go from the coefficients of a balanced chemical reaction and just dump them into a rate law. It needs to be found out experimentally. If you know the molecularity of a reaction, though, you can actually, without doing experiments, know its rate law. And this is going to be a fundamental idea of reaction mechanisms and molecularity. So if we look at the first one, a unimolecular reaction, where we had this excited state, ozone, where it just spontaneously breaks apart into O2, and O2 being molecular oxygen and atomic oxygen, the rate is equal to some constant, directly just O3 raised to the first. It is a first order reaction. Bimolecular reaction, again, here's our non-excited state ozone reacting with atomic oxygen to form 2 moles or 2 atoms of molecular oxygen. The rate is directly proportional to the rate constant times O3 raised to the first, which is its coefficient, times O raised to the first, which is its coefficient. Again, we see in a termolecular reaction, 2 atomic oxygen plus 1 metal gas is going to yield O2 gas, molecular oxygen, plus the metal gas. The rate constant, again, is rate equals whatever the rate constant is times O, the concentration of O, raised to the second, because there's two of them, so there's a coefficient. We could write this easily as 2O plus M. So O raised to the second times M to the first. So unlike balanced chemical equations, which we do not know if it's an elementary reaction or not, we cannot predict the rate constant. But if we do know the molecularity of a particular elementary step, we do know the rate constant. And that's our take-home message from this. So this is just a slide showing different ways in which you can achieve a unimolecular, bimolecular, or termolecular reaction, and different ways that the rate law can be expressed. What I'd suggest is, for this first 21 minutes of the lecture, putting everything together, or at least the part about molecularity. This chart should make 100% sense to you from top to bottom. If that doesn't make sense, go back, make sure it does. If it doesn't still, come to class on Friday with questions ready to go. But I'm saying, at this point, you should be able to understand from this point down to this point, and everything in between should be internalized at this point. All right, so what happens then? We've been talking about having different reactions, different elementary reactions that build up to an overall reaction. Well, what's actually determining how fast that reaction is? If I have two Ks, well, that's really confusing, because everything I've been reporting thus far only has one K, right? We look at everything in rate law, there's only one K. So what K is that reporting on? So the way we simplify these reactions is talking about a rate determining step. And so mathematically it's simplified, usually almost always the case. In actuality, the rate determining step automatically simplifies and determines the rate of the reaction. There are, again, always exceptions to the rule, but usually the rate determining step is going to be your K. Right? So it's the slow step in a reaction mechanism, since it acts as a bottleneck and limits the rate at which the reaction can be converted to products. So let's take an example where, excuse me, with the very first reaction. So we're going back to our NO2 example. If the very first reaction is the slow step, so that means if we're comparing K1 to K2, K1 is much, much, much smaller than K2. So let's think physically what's happening. Basically that K1, remember, it's related to its orientation and its activation energy, is saying that it's less likely to happen than an NO3 to successfully collide and react with the CO. So that's saying that the probability of these two colliding with the correct energy and the correct orientation to form these intermediates is much lower than this. And so this is where the idea of a bottleneck happens. So if K1 is much smaller than K2, what ends up happening is we start producing small amounts of these, because this reaction is really not that successful. As soon as one of these NO3s is produced, if this K2 is much, much faster than K1, essentially, not instantaneous, but it's really, really quick. Right? As soon as this NO3 is produced, it collides with the CO and immediately goes to product. There's no reverse step. Right? So it collides, it takes a while, it's got to find the NO2, it's got to be the right orientation, it's got to be the right energy. Finally it forms NO3, and it's just quick, it just goes. So there's our fast step. So again, this is our idea of the bottleneck. It's slowly, slowly trickling through NO3, and as soon as that NO3 reacts, it just goes. And so what we're going to notice is that this fast step, in the end, because it is not rate determining, is actually not part of the rate expression. Instead, what we see, the rate expression, so our our rate equals K times whatever, right? Our rate law is based on the slow step. So what that means is, even though our overall reaction here shows we have a coefficient of 1 in front of the NO2, and a coefficient of 1 in front of the CO, CO is actually not part of that rate expression at all. It's not part of the rate law. Instead, what we see is rate equals K times NO2 squared. And you'd say, wait a second, if I was just looking at the overall reaction, there's no way in hell I'm getting to a square here. How does that happen? Well, it makes sense if we break it down into our elementary reactions. When we see here, two of them needs to collide. So if we increase the concentration of NO2, right, because there's two of them need to collide, that means the rate quadruples. It goes up by a factor of 2. That K that we solve for is actually only K1. K2, we need to set up a different experiment in a different way to solve for K2, but the K in front of it ends up just being K1. So the overall rate that determining this, because of that bottleneck in the slow step, is just the rate times whatever this first forward reaction is, K1, times the concentration of the NO2 squared. So let that sink in for a little bit, because that's our first example. Slow step, the K is K1, and it only depends on the molecularity of the very first elementary step. We kind of went. So we have a new example now, sorry. We have, instead of NO2 reacting with CO, we now have the degradation of NO2Cl, a new gas, right? It's going to have a two elementary step reactions where it says K1 describes the reaction in which NO2Cl decomposes into NO2 plus Cl, so atomic chloride gas. And then the next step, where that chlorine gas or the Cl gas reacts with another molecule of NO2Cl, has a new rate constant of K2, so it happens in a whole new elementary reaction to form NO2Cl2. So the first thing we can do is double check to make sure everything cancels out. Well, alright, well my NO doesn't really cancel out, so there's two of them down here. Okay, cool. The Cl does cancel out, that's an intermediate, so we do not see it in its overall reaction. So when we add everything up, NO2Cl plus NO2Cl, well, there's my 2 NO2Cl. The NO2s didn't cancel out, that plus that, no, it's 2 NO2. The Cl's did cancel out, forget that, and we just left with Cl2. So this was the overall reaction. If I put this in under the reaction conditions, I would get this out. But let's break this down. The first question is, what is the molecularity of each step? So we need to break down each elementary step and not the overall reaction. First step, K1. We have a first elementary step. Take 2 seconds, think about it. What do you think the molecularity of that step is? Take a look at number 2. K2 represents the second elementary step. Again, take 2 seconds, think about it, say it in your head. What do you think is the molecularity of that step? It's not going to be written on the screen, but the molecularity of the first step, the K1, the slow step, is 1, is a molecularity of 1, because only one product is decomposing, so it breaks apart, does not need to react with anything else. We look at K2, 2 different molecules, or in this case an atom and a molecule, need to collide. So that was a molecularity of 2, so we have a unimolecular and a bimolecular reaction. So we don't attribute molecularity to the overall reaction, only to elementary steps. What is going to be the rate law? That's an interesting question. So I'm going to leave that up to you to solve. I realize I've been holding your hands, not in a bad way, but there's a lot of times where it makes sense when I explain things to you. I will put this on EC Learn, what the rate law is for this reaction, but base this off of the last reaction that we did. When we see that the rate law down here is based off of the slow step times the molecularity of those particular reactants. So again, give yourself some time, think about what the rate law is for this, and I'll post it on EC Learn, most likely tomorrow night, because our quiz is going to be on Friday. Right? And so the last part that's asking us, if we observe the overall reaction, what plot would give a straight line? Again, since this is old hat, hopefully at this point, because we were just talking about this for the last couple of lectures before and after spring break. Figure out, based off of your rate law, which of the three ordered reactions do you think it would be? Would it be a zeroth? Would it be a first? Or would it be a second order reaction? So now we're seeing from this particular question, we've now incorporated the new term of molecularity. We've now seen from elementary steps how we can add these elementary steps together, figure out, experiments with to figure out what's the slow step, but once we know the slow step, we can figure out the rate law. And then from that rate law, we can also figure out what order overall the reaction is going to be. Zeroth, first, or second. So now we've started to build this up. We're pulling everything together. But what happens when we get even more complicated than just the slow step is first, right? We're down now, so look, this is actually a pretty complicated example of a multi-step reaction with initial fast step. So most of you are biologists, and you're going to find out that majority of enzymatic reactions end up happening in this particular order. Usually the fast step and a reversible step is the first process. Again, I'm assuming, I hope a lot of you are, hopefully all of you are chemists, but I also understand reality that a lot of you are also biologists. When you think about two molecules coming together, like a protein and its substrate, that protein needs to bind to the substrate, and then sometimes it lets it go unsuccessfully reacting. And that's what this first step usually is represented in biology, a fast step and reversible. This makes your life so easy in biology if this is the case. If it's not, you're going to have a hard time. But luckily for us, most steps are like this. So let's take an example of just a chemical step, though, in which we have a first step and a reversible step, which means, so actually we got to break that down, right? If we take this reaction, so we'll look at the overall reaction of 2NO plus 2 molecular hydrogen producing N2 and H2O. That's our overall reaction. But let's break this down. It's saying the first step is reversible, in which 2 NOs combine in the correct orientation with the correct energy to form N2O2. What this represents right here is that there's a very fast first step in which the NO reacts to NO2, but also a very fast reversible step in which that molecule is unstable and breaks apart. What this means is, usually within a couple of microseconds, that this equilibrium is established, in which the rate at which this forms equals the rate at which it breaks apart. So this is going to kind of be like a red herring. This is what we'll be getting into in terms of equilibrium in the next chapter. We'll be dealing with forward and reverse reactions, but assume that as soon as this one forms, it's breaking apart, and we end up within a couple of microseconds in a pretty stable population with both NO and N2O2 and a stable concentration. So that's what that means. It goes forward, it goes back, it goes forward, it goes back, and it's continuous. This was our definition of dynamic equilibrium from 1101. All right, so let's move on from that. That was our new terminology. Hopefully it's not too hard to internalize on that one. So once that N2O2 is formed, right, it's going to react with this molecular hydrogen. And this is the slow step. This is our rate determining step. So this happened really quick, hit equilibrium really quick. So it's almost a constant population of N2O2 based on NO. So that new constant population is now reacting with the molecular hydrogen, and this is our bottleneck. This is the slow step. So that means this happened really quick. This happens slow. So there's a rate at which this N2O2 or N2O is formed, and the water is formed, and then we have another fast step preceding that. So really, really quick, we establish a new population of N2O2 really fast. It's pretty much in equilibrium. Now it reacts with H2. That's slow to form N2O. And then this next step is faster than that slow step. So as soon as the N2O forms, boom, forms N2 and H2O again. So now let's add everything up. I'm going to leave that up to you. It's a little bit complicated with three of them. Make sure you're crossing things off that are on both sides of the equation, but what you should end up with is the overall reaction, and you're going to find out that the rate determining step, again, has nothing to do with your starting products, and in fact, look at this, it has nothing to do with NO at all. In fact, the rate is proportional to the concentration of this first intermediate raised to the first power times only one of the product raised to the first power. So it ends up being a second order reaction, but overall this K2 describes and limits the entire reaction. So the slow step in a multi-step reaction, the slow elementary step, is the one that is going to determine, and in most cases, not always, you can always break the rules, what the slow step and what the rate of a particular reaction is. So this one I feel like really encompasses everything that we've learned so far. Right? It's brought into the fact that we have a balanced chemical equation, right? We have rates that we've determined for all these steps, probably by doing independent experiments. We figured out the molecularity of each step, and we found out once we know the slow step, we've now defined the rate. So let's start to link this together. So what I'm trying to do now is we've kind of ended this whole talk about reaction mechanisms, in which the take-home message being is the slow step determines the overall rate law. Just because something is part of the reactants does not necessarily mean it's going to be part of the rate law. It all depends on the reaction mechanism, right? That's that take-home message. Slow step equals rate law. Molecularity of the slow step are the exponents of the rate law. So this last bit that I'm going to touch on is just going to be a little bit of review-ish, trying to tie into the Arrhenius equation that we talked about on Monday, right? So we've pretty much beaten it to our heads at this point that typically as the temperature increases, we're going to learn exceptions in the future, that this is not always the case, but typically. As the temperature increases, the rate of the reaction increases. So we take, again, we'll have the N2O5. It's saying two of those moles, or two atoms, or two molecules or 2 moles react to form 4NO2 plus O2. And you find out the rate based on the reaction mechanism. We could pull this apart. It's dependent only on Kn2O5 to the first. And again, rate is dependent on temperature. So again, we looked at this slide before, so let's just, this is kind of a review at this point. Let's just ride through it. We talked about there's certain reactions that we talked originally when I gave you guys in class was talking about, well, why does hyperthermia or why does hypothermia kill you? Well, being cold is not necessarily deadly, but what is deadly is when your internal body temperature drops to a certain coolness or coldness in which the rate constants in your body of all those molecular reactions becomes out of sync and out of the correct rates, so they're all slowed down. It starts messing up the concentrations of the molecules in your body, and that's what ends up killing you. All right, you're not reacting as quick, so the equilibrium of all the biological molecules in you can end up being perturbed and into a point where it kills you. Right? The less dramatic example is this magnesium example that I gave you, in which if you took magnesium metal, so usually filings, and you throw them in cold water, nothing happens. You heat that up, and all of a sudden magnesium starts to react with the hot water. So the magnesium's not really doing too much. It's a solid. It's just kind of sitting there. And we talked about, well, if we're heating things up, right, we're giving more energy to that system. So the magnesium, we talked about energy being kinetic energy. So magnesium doesn't really have a lot of place to move. It kind of vibrates in space, but it's a solid. But that heat is being transferred to the H2O, and it starts to move quicker. And we know moving quicker also gives it higher kinetic energy. And this is what we talked about before when we linked vapor pressure to overall kinetic energy of a molecule. So we know now that temperature is not just we don't have one number to describe the temperature of each molecule in a sample. We know that it's going to be based on a distribution, an average distribution of kinetic energy of the molecules. right? And so this is based on our collision theory. So if the average kinetic energy, or just the energy in general of particles, increases, the average molecular speed increases. So that was our old way, not old, still true, but that's the way we described it before in terms of vapor pressure and kinetic energy and temperature. The new part to this is that the collision rate increases. And we originally described this in class by talking about, if we're in a certain classroom and there's, 20 to 40 of us, we're slow walking, we can kind of avoid each other. Every once in a while we bump into each other, we bump into the walls, whatever. I ask you to fast walk or run, all of a sudden there's more likely a chance to you to bump into someone unintentionally. And that's the same idea that we see here. So what we see is a fraction of collisions on the y-axis and collision energy, which basically does translate to kinetic energy directly on the x-axis. So what we see here is that we have two curves, one in purple, one in blue, that describe the same number of particles. So the area under the curve of the purple curve is the same as the area under the curve of the blue curve. At a low temperature, most of the molecules in that sample statistically will have an energy somewhere around here. It's a general graph, it's abstract, I don't know what that energy is, but it's pretty low, right? What we notice though is when we increase the temperature, so the probability of being a molecule having energy down here decreases significantly, but we notice on the far end of the graph is that the probability of having energy that is higher has now been raised up. And just like when we're talking about vapor pressure, we can talk about activation energy. So it's the minimum amount of energy to do something, right? We talked about the minimum energy needed to break the surface of the liquid water and enter a vapor phase, and that was contributing to evaporation. Right, so it's a statistical probability that a particular molecule would just have the energy to break free. The same idea happens here when we're talking about collision theory in terms of reactions. As the heat goes up, if this is the minimum amount of energy that a reaction needs to have to successfully occur, if you increase the heat, well, look at this, the probability of all these molecules. So you're looking at the area under the curve from here to basically infinite energy. So you integrate under that curve, you get an area under here. So the purple area, which actually goes all the way down to the axis, is much bigger than the blue area under the curve that goes down to the axis. So statistically, there's much more particles that have at least the activation energy or more at a higher temperature than does the lower temperature. And this brings us back to that transition state that I was talking about earlier. And this also leads us into the orientation. So if we have A plus is a new molecule called BC, right? It needs to react in such a way that's going to form AB plus C. So there's our A plus BC plus AB plus C. We talked about having two things. Minimum, the energy. So if there is a successful collision, that's what we're going to assume first of all. There needs to be a minimum amount of energy to reach the transition state. And the reason why it takes energy, so if we think about that, right, we've talked previously that breaking bonds always takes energy, right? That's why I keep asking it on the quiz, and I even asked it on the exam, right? Breaking bonds always takes energy. So to even think about forming a new bond between A and B, this bond between B and C has to be cleaved. That always takes energy. So EA is always positive. It is never negative. So what we see here is that the bond between BC is breaking and the bond between AB is starting to form. So actually on this side of the curve right here is only the breaking. On this side, this is when AB starts to form. So that's why it is always positive. This is the breaking, hits the transition state. That's why you see it kind of looks equidistant, equally formed, and then it starts to form. Right? It's not dependent on time. It's very, very rapid. And that's why transition states usually cannot be isolated. Also in the fact that you have half a bond being formed and broken. But what we can do is theoretically, in our thought experiment, graph it on our energy diagram which we know the transition state is higher. So the energy it takes to go from the pure reactants up to this transition state, that's our EA, so that's our barrier that we need to overcome. And then we proceed rapidly down to form this new molecule, AB, and then C goes off on its own and does whatever it wants to do. The difference between the reactants and products, as always, and we've done this several times with their energy diagrams, is just delta E, right? When we do an enthalpy diagram, imagine all of this was released in heat, well, that would be delta H. But we're being generic here. I don't know if this is released as energy. I don't know if it's released as heat, entropy, there's a lot of things. So we're just generally calling this delta E. But if this was done under constant pressure conditions, this would just be delta H. We put this all together. So we were talking about what's happening on the microscopic level and how do we put the Boltzmann distribution, how do we accurately model that, plus accurately, or at least give terminology or define what these certain variables are and how they impact how fast a reaction happens. So we know K is our rate constant. That is the number that tells us how fast something happens, molar per second. And then we talked about A, right? The collision frequency factor. And this goes back way to the beginning of the talk when I was talking about how, well, hold on for a second, we're going to go on for a ride. It's going to take a bit. Go all the way back to the beginning and we look at this step in which these two NO2s needed to be oriented in the correct three-dimensional space in order to react. If this N collided with that N, so imagine if you had two of these, but the O's are hanging out over here and the N's collide, that's not successful. The two N's will not bond to form this reaction there. In fact, I can guarantee you they will repulse each other, at least under most reaction conditions. So that is our A factor, collision frequency factor. How often do successful collisions happen? They need to be in the correct orientation. EA, right, we're up here. That is our activation energy. What is the minimum amount of energy when these two combine in the correct orientation needed to achieve that transition state and turn into products? And then we're just down to our our boring old terms that we've used in 1101. R, which is our gas constant. Again, we have a lot of numbers for gas constants. It's up to you to determine which gas constant to use, right? There's different numerical values, but they all have different units, all of them describing the same thing. R is our go-between between the microscopic level of energy and the macroscopic concept of temperature. It's just a go-between. So typically we use the 8.314 joules per mole Kelvin, and then usually in the ideal gas law we'll use the 0.08206 liter atmosphere mole Kelvin. So just keep that in mind. Temperature, again, there's certain equations that only function when temperature is in Kelvin. So keep that in mind. Again, if we go back and look at these curves right here, this would represent a temperature of 0. Well, 0 Celsius is actually pretty hot compared to absolute 0. So this whole graph right here, the Boltzmann distribution, is based off of absolute temperature. So this is absolute 0 right here. That's why there is the fraction of collisions is 0, and the collision energy is 0, because the temperature is 0. So it absolutely needs to be an absolute temperature. We did this before. We rearranged the equation by taking the natural log of both sides. We're able to linearize the information. So the ln, the natural log of k, equals negative EA over R times the reciprocal of absolute temperature plus the natural log of A is going to give us a linear version, or a linear way to process our data in which we can easily extrapolate the activation energy of a reaction. So this is actually pretty useful because if you think about it, when we look back here, where'd it go? Excuse me. Right? The EA is only based off of successful collision. So what happens if you don't have a successful collision? Isn't that going to, muddy your data a little bit? Because not all the transitions, or not all the collisions are successful. And so that's a really good question. Like, well, if half my collisions aren't happening, isn't that going to mess up how I'm going to calculate EA? And what we see is actually we can actually basically get rid of this term. It is our y-intercept, but as long as we know the reactant constant and how that varies with absolute temperature, we can extrapolate the activation energy, the barrier that two particles minimum need to have this reaction happen, without even taking into account how frequently they collide. So that's actually, it seems trivial, but it's actually a pretty powerful equation to calculate the activation energy, because A is not the most intuitive thing to calculate, but now, based on this equation, we can even calculate A. Once we know EA, there's our y-intercept, we found our natural log of the collision frequency. So graphing it this way is pretty powerful. So let's finish this off. We've talked before about catalysts. You'll be using catalysts in lab this week when you're looking at the reaction of iron in the form of steel wool and how it reacts with oxygen. We know that forms rust. It's really slow. We'll be adding a catalyst of acetic acid. And so let's talk a little bit more about what acetic acid, not acetic acid, but what catalysts do. All right, so let's read off our definition. It says a substance that increases the rate of reaction without itself being consumed in the reaction. Okay, well that makes sense. So if I have it part of an elementary step, that means in the end, it shouldn't actually be part of the reaction. Okay, that's rule number one. A catalyst is used in one step and regenerated in a later step. Okay, that would also make sense with our original definition. Again, I recognize a lot of you are biologists, or plan to be biologists, so think about in terms of proteins. I can only think of one example of a protein that is not a catalyst, that actually does chemical reactions. Look up, I gotta remember this one, uses biotin, gotta remember which one it is. I'll figure that out later. But most enzymes, so any protein that does a catalytic reaction or an enzymatic reaction, a chemical reaction, is called an enzyme. That enzyme in the end is left unchanged, so that's why we call enzymes catalysts. They speed up the reaction, they take it through a different reaction mechanism, but they're never consumed. And if you're interested, I'll figure out what that other enzyme is. It's something that uses biotin and a bunch of sulfur. Forget what it is, but it's a really weird and rare enzyme, and it's still under debate if actually it's a catalyst or not. But it looks like it's actually a substrate. But let's get back on track. So we're talking about catalysts in a chemical sense, not particularly in a biological sense. So let's take a look at the breakdown of hydrogen peroxide. So here we're down at the overall reaction into water and oxygen gas. So it's kind of a slowish reaction. I actually don't know what the half-life of the reaction is, because if you look, it's first order. You could figure it out, but if you have a bottle of hydrogen peroxide at home that treats wounds, it doesn't last that long. It lasts a couple of months, right? If you added iodine to that, it's going to last less. So let's figure out why. And the reason for that is that it actually introduces a new elementary step. Instead of just directly breaking down into water and oxygen, the iodine ion reacts with the hydrogen peroxide, the H2O2, to form water and an IO1- intermediate. So again, like we talked about before, well, here's our catalyst, so everything in bold is our catalyst. It actually physically reacted with our product, which all catalysts do, and even the same thing with enzymes. It has to physically touch and interact with your reactants. But then we see that it's immediately reacted with another molecule, peroxide, to form water and O2 gas, and it regenerated our catalyst. So even though it was part of the reaction, overall it was never consumed. And if you put it through like a mass spec or some other instrumentation that could measure how much I1- is there, it'll never change, beginning to end. Oops, what's it doing? Here we go. So overall, if we add up our elementary steps, we end up with overall the breakdown of H2O2 into water and oxygen gas. So that's what we see over here. There's our hydrogen peroxide. There's some activation energy associated with that to break apart spontaneously into water and oxygen. What the presence of iodine does, again, is breaks it into 2 elementary steps. So we see step 1, step 2, step 1, step 2. So the first part, we have this activation energy, right? We cannot isolate a transition state, but here are our intermediate products. Go back, there's our intermediates, water and IO1-. So water and IO1- exist here. We'll look at that and look at this EA right here. Remember, we're going from what we consider our products to the new transition state. That is a small jump. So that means this next step is going to happen much faster, and then we've regenerated our catalyst, and we still form the same products, water and oxygen. But if we look through it, and we went over this before in class, but that definition that we had in high school, the catalyst lower the activation energy, is categorically false. Well, I mean, I hate saying that way. I mean, your high school teachers were telling you a half-truth, I guess, is maybe not categorically false, but the activation energy is lowered, but it's not this particular reaction got lowered. It's not like it took this activation energy here and brought it down. The catalyst takes it through a separate reaction mechanism, and that particular reaction mechanism just happens to have a lower activation energy. That is why it's a catalyst, because A, it lowers the activation energy and it's not consumed. So so imagine going through, if this was the path of going over a mountain, so you had to go over the summit, this is like kind of just skirting around the edge, right? Maybe there's 2 smaller peaks that you can go up the same path, and you're like, oh, hey, I'm going to go take this different route, and I'm going to go over 2 smaller peaks, and I'll get down really quicker, rather than going all the way to the top and then coming back down. So you start and end in the same spot, but the path that you took is different, and the catalyst takes you through a different path. It's like a guide that knows the shortcut, and so therefore it lowers the activation energy just because it gave you a shortcut through a different reaction pathway. Again, we look at that, so if we're going to try to figure out what the rate determining step was, and this is a little bit new from last week, right? So since the catalyst is involved in the rate determining step, it often appears in the rate law. So we look back here, based on this particular reaction, right? Here's the rate determining step. Well, it was the first reaction. Well, the catalyst was part of the rate determining step. Whoop, right there. We know this little bump, because it's so much faster, is not taken into account in the rate law. So here, this will define our rate law. We take a look at it. Here's our rate determining step, our slow step. Well, that's going to determine my rate law. Well, let's take a look. Rate equals K, which is our proportionality constant, our rate constant, times the concentration of H2O2, right? We have a coefficient of 1 plus I1- with a coefficient of 1, so both are raised to the first power. We have a second order reaction that is entirely based upon the concentration of H2O2 and our catalyst. None of these intermediates, and especially, even look here, you see we have a coefficient of 2, doesn't matter. It's H2O2 raised to the first because our rate determining step only deals with 1 molecule of H2O2. Take a look at that. Basically, our summarization right here. I think what I'm going to do, this is a little bit more involved and requires a little bit more math on the board. What I'm going to want to do is on Friday, I'll finish off with, or start up with this, just to show you how when you have certain reactions that happen with certain intermediate steps, it's not as straightforward. Sometimes it can be, but it's not as always straightforward to pull out the slow step as the rate determining step, though it usually is. You can sometimes, but sometimes one of those compounds is an intermediate, and you can't always quantify how much intermediate you have. So we'll stop here. We'll pick up with this on, so if it's the Wednesday class, we'll pick up with this on Monday. If it is the Monday, Wednesday, Friday class, we'll pick up with this on Friday. Alright guys, it's been about an hour. Hopefully you sat through the whole thing. If not, take some break, grab some food, grab some coffee. I will see you all whenever the next time we have class. So I hope you enjoyed the day. Hope you enjoyed the lecture. I'll see you guys soon. Bye.